Okay, thank you everyone for joining the NASA Carbon Monitoring System CMS Policy Speaker Series. We're gonna start in a few seconds. We see that people are joining in. I'm gonna give a brief welcome and announcements, and then we're gonna have today's speakers presenting. Um, just gonna share quickly the screen. So we can start first of all. I would like to send along the regards and excuse the CMS science team lead George Hurt, who couldn't be today in this talk. Today's talk is titled "Searching for Sanctuary: Lining Up Old Growth Forests and Carbon Reserves with Fire Refugia in a Changing Climate." And this talk is going to be given by Raymond Davis and Sikian Yang, both from USDA Forest Service. Before moving to the talk, I would just like to make some brief announcements regarding the CMS initiative for those of you who don't know. Um, as I mentioned in other talks, we do have CMS data products that are already available, to be used. They're archived. Here, I'm just highlighting some of the newest data sets related to biomass that we have archived at the Oak Ridge National Lab DAC.
You're not in full screen.
Okay, let me see now. Can you see it now?
You have to switch the display, swap
Let me do that.
displays.
Usually, when I do that in WebEx, the computer goes crazy. Uh,
Go go one button to the left and swap displays.
yeah, let me see because now the computer went. Can you see it?
Yeah.
Okay, perfect. Thank you. Um, so here I'm just highlighting some of the newest data sets that we have archived Oak Ridge National Lab DAC. So from terrestrial carbon stocks emissions and fluxes in the contiguous US, this is a project from Sasansachi to forest carbon stocks and fluxes, also in the contiguous US. This is a CMS project from Christopher Williams. Two LiDAR-derived forest above ground biomass maps in northwestern US, where the talk today is going to be focused. And this is a project from Andy Hudak. I also wanted to, for people that don't know, to pay attention to this, how we engaged originally with Raymond Davis at the USDA Forest Service was during this USDA Forest Service NASA partnership that began, I think, around 2018, 2019 with a workshop in Salt Lake City. Now this has transitioned and we have continued this effort with the U.S. Forest Service, and it's called the Applied Earth Observations Innovation Partnership. Um, so I have included here the website. I'll copy the website link in the chat box. If you want to take a look there, you're gonna have the past meetings, the reports, and some of the upcoming events that we have. Um, and I just wanted to mention that this collaborative venture is bringing together representatives not only from the U.S. Forest Service and NASA, but from other relevant entities and U.S. Government agencies. And the activities and the events have provided an opportunity to increase the awareness of the application of Earth observations data in support of land and natural resource management goals. As always, if you want to have more information about CMS and some of the projects, including the new projects that were funded now in 2020, you can go to our website, carbon.nasa.gov. We have the science team meeting coming up virtually November 16 to the 18th, and you can find more information coming up on the website. Also, as a reminder, we have an ongoing call for papers for a special issue of the journal Environmental Research Letters. and this one is focused on carbon monitoring research and applications. The call is staying open until the end of this year. So if you're planning to draft a paper related to carbon monitoring or any of the topics that you see there, biomass, atmospheric flux, quantification, uncertainty, even about user applications and stakeholder needs, please consider this a special issue. Um, so now I would like to introduce today's speakers, Raymond Davis and Sikian Yang. Raymond is the monitoring lead for the Old Forest and Northern Spotted Owls for the Northwest Forest Plan Interagency Monitoring Program. And Sikian is a computer scientist at the U.S. Forest Service Forest Inventory and Analysis Program, and he focuses on applying remote sensing for ecological applications. Um, I'm gonna stop sharing my screen and now leave you all with Raymond and Sikian. Raymond, let me know if you can share the screen.
How does that look? Are you seeing my screen?
Yes, it looks good.
Perfect.
Okay, good. All right. Well, thank you, Adil. Thank you for this opportunity. Also, CMS, thank you for the opportunity for Young and myself to share some of the work that we're doing over here in the West Coast of the United States. The title of our talk is Searching for Sanctuary, Lining Up Old Growth Forests and Carbon Reserves with Fire Refugia in a Changing Climate. I'm going to go over the first half of these slides, and then Young will take over and finish them up. So before I get into the slides, I'd also just like to thank everybody else who has the interest to listen in on today's slides. And with that, I will start with the first slide. Let's see if I can get it to go. Yeah, okay, there you go. There's a little lag on my end. Okay. So this first slide will give us a little bit of geographic context of where the Northwest Forest Plan is that we're going to be talking about today. And so if you look over in the west coast of the United States, that green outlined area is the range of the northern spotted owl. That is what defines what we call the Northwest Forest Plan area. The owl was listed in 1990 as threatened under the Endangered Species Act. And so we've been tracking what's going on with its habitat and populations ever since. This next slide shows you that the range of the owl overlaps that part of the United States, the lower 48, that has some of the highest above ground carbon forest biomass. So the juxtaposition of a threatened species with a lot of carbon and the resources, the timber resources associated with that is an interesting juxtaposition. Let me just put it that way. These next slides are what I consider the first Forest Time Series maps for the lower 48. And these maps were put together by the chief of the Forest Service, William Greeley, back in 1925. So way before satellites were orbiting the Earth. And this paper that he put out was about a relationship with the timber supply in the United States and the geography of where people were settling. And so you can see that by 1850, the early part of the European settlements of the continent, the timber supply had decreased. The term virgin forest here represents the natural stands, the old growth stands that existed prior to the settlement period. And then by 1920, it looked like that. So there was timber famine. There was a concern of lack of timber supply nationally. It was already happening in the East Coast, and most of the remaining timber supply was in the West Coast of the United States. These three maps resulted in the initiation of an inventory of the forests in the United States by the Forest Service. That happened in the late 1920s, and the fieldwork happened in the 1930s. I'm going to jump to the results of that, and this is a map based on satellites, MODIS, moderate resolution satellite, and FIA forest inventory and analysis plot data. So this is what we're using today to monitor forests. you can see that the map from 1925, done with all that technology, actually looks pretty similar to the map of today. I'm getting a little background noise. I was wondering if folks could mute their mics. Thank you. This next slide shows you the juxtaposition of the carbon of today on a map made from different technology that predicts where wildfires are most likely to occur. So the red areas are the places where the model predicts the occurrence of wildfires, and the blue area is less frequent occurrence. And so you can see how those overlap the carbon. And this is all the fires going back half a century. So you can see that the model produced by the Forest Service to predict wildfire occurrence actually works pretty well, especially in the West Coast. And so what we tend to focus on as managers and just in general are the redder areas, the places that are always burning. And so the headlines, you're seeing them today about the fire coming into the Sequoia National Park in California, are mostly about what's happening. Forest fires burn millions of acres in the West. You never see a headline for the blue areas where nothing's happening, and it's literally like watching trees grow. You see forest continues to sequester carbon in the West. That's not a headline I've ever seen. And so what I'm going to try to do today, what Young and I are going to try to do today is to highlight the blue areas on this map. Because it seems like most of the time we're going after the smoke and we're chasing the smoke. And in 2020, last year, that was the year for the books. We had a lot of huge fires in the West Coast that were of very high severity, putting smoke all the way from the West Coast to the East Coast. These fires were on par to hurricanes that happened in the East Coast. And not to mention that this was the first year of the pandemic, so it was quite an interesting year last year. So now I'm going to zoom into the Northwest Forest Plan area and give you a little bit better understanding of what it's about. This is, again, the range of the northern spotted owl. There's about 50 million hectares of forest land within that footprint. About half of that is managed by the federal government. That's the green areas right here. This is a map of old growth in 1940, so you can see that not the entire forest was covered by old growth. In 1940, there were patches and pockets of it in between fire footprints from the past. This is what it looks like as of 1993. 1993 is the year that the Northwest Forest Plan was designed, and then it was implemented in 1994. So you can see in this map over here, most of the remaining old growth occurred on the federal forest footprint over here. So if you look at these two maps, you'll see a lot of similarities between the two. This last map shows what the Northwest Forest Plan is trying to achieve, is this well-connected network of older forests on federal forest land by the end of this century. So they established this network of large forest reserves, we call them late succession reserves, with the goal of maintaining the existing old forests within those boundaries and to restore younger forests within them to an old forest condition by the end of this century. That's kind of what we're hoping it looks like. Trying to advance my slide, but it seems to be stuck. Let me try the arrow keys. I apologize. The slide's not advancing. All right, let me try to escape from the PowerPoint.
Ray, if you can also sometimes if you turn off your camera, I think it might work better. You can check that.
All right, let me try that. Oh, yeah, okay, that seemed to show. Okay, good. Thank you, Neil. So, all right. So the monitoring program is tracking what's going on with old forests within those reserves. And so here we see a long-term trend, the green line of this is northern spotted owl nesting and roosting forest. So this is basically old growth forest. You can see the tail end of the decline prior to the listing of the owl in 1990, and then when we stopped cutting timber as a result of the timber injunction, it starts to grow back. Northwest Forest Plan was designed here, and then over the first 25 centuries, we see this period of maintenance and restoration within the reserve, which was what it was designed to do. So at the 25th anniversary, everything was looking good, but after the 25th anniversary, we see this declining trend over here. That is a result of, on the bottom here, you see the occurrence of large wildfires. And so you can see here in the last few years, we've had a lot of big wildfire seasons. And then this year, we have another one, and it's still burning. So that right now, it's a little over 1 million acres, and we'll see where it ends up by the end of the year. So we are interested in to see if whether this declining trend will continue, because currently we now have less old forest today than when we actually when the owl was listed and when we designed the Northwest Forest Plan in 1993. So that's not where we want to be. So to get a handle on this, we started looking at the occurrence of large wildfires, and that's usually what's taking the forest down. And so here we have a series of what we call normal fire environment maps. And so this is based on climate normals. The red areas are places that burn frequently. The blue areas are predicted to burn less frequently. So these are very similar to the national burn probability maps. They're just of finer resolution. And also we incorporate NASA NEX downscale climate predictions to see what that pattern might look like into the future. So this is the first climate normal period. All these fires fill the redder areas as the model predicted. This is the current fire season. So you can see some fires here within Northern California and then the Cascades in Oregon. And so what we anticipate is with time, that red area, those redder areas are going to expand, and the bluer areas, the places that burn less frequently, are going to contract. And so that's a concerning trend that has pushed us to collaborate with various partners. Oregon State University College of Forestry has established a fire refugia project. Cameron Nafisi is the lead analyst. Meg Krawczyk is one of the principal investigators on it. Garrett Meigs from Washington State Department of Natural Resources used to work for OSU, now working for the state of Washington. David Bell from the Forest Service Pacific Northwest Research Station, and others. We're also collaborating with the Oregon Department of Forestry, or Andrew Yost, who's the forest ecologist. He works on Oregon forest carbon policy issues. And then with Rocky Mountain Research Station, Sean Healy and Shushang Yang, who will talk about the remaining slides here. I'm going to turn off my mic. Yeah.
Hey Ray, we need to use your slide. My computer does not allow me to share my screen.
Okay, well, I got the first slide up.
Yeah. Hello everyone, thank you for joining us, and thank you for allowing me to present this our work here. So as Ray introduced, we want to look for fire refugia. This is the I only see partial screen. Is that the
Ray, the windows you have open, there you go. That's good now. You can't have a window open over the slide while you're displaying.
yeah, this is good. This is our result to show the fire refugia through this modeling process. This go to the next slide, Ray, please. So what first of all, define what is the fire refugia that we're trying to map. So there are two aspects with it. One is it's not burn, unlikely to burn, that's a low fire frequency, and the other part of it is low fire severity. So when it burns, it's unlikely to burn at a high severity. So it provide a refugia for species for vegetation. So this is the definition we used for our mapping. That's our target population we want to find. Next slide, Ray. So there are many different factors that can affect the fire refugia. So the first we show that the low frequency and the low severity, that's one aspect of it. The other is fire refugia is whether it's a predictable refugia and also the stochastic refugia. And on top of that, there is another aspect of it is ephemeral refugia. So for given the refugia for not a different fire is not the refugia. So there's ephemeral and persistent. So that's translated this on the basically ephemeral is more operating on the local scale, small scale, affect topographic factors, local weather, and the fuel condition. On the persistent long-term refugia, our concept is it's the topographic environment provides a template, then climate operates on that combined with vegetation component that will have the persistent or long-term refugia concept. So in the end, basically the following equation, this is our conceptual model. Refugia is a function of a topographic variable, climate, and vegetation. Trying to find refugia is trying to implement this equation to find out where they are. Next slide, please, Ray. So Ray showed the climate norm. That is the fire refugia condition on the climate condition. So Ray published this paper in 2017, described this. This is the one aspect of the refugia. So when we use this data directly, we're not trying to remodel that. Next slide, please. So the second component is vegetation. So as Ray described earlier, trying to make a late succession reserve for the future. So what's the vegetation condition for the future? In what I'm going to present here, we are not explicitly considering vegetation. Table is the linear group to predict the future vegetation. In this work, I'm proposing the probability of fire refugia based on vegetation is mainly one binary vegetation condition, is whether it's forest covered or not. So next slide, please. Sorry. So the focus will be on the finding refugia from the topographic variable and basically the topographic template of a fire refugia. So our method is using historical fire. As I described earlier, there is a ephemeral refugia. So because each year there are different fires. They have a different area burned, a different area not burned, and different area with different severity. So we want to locate the low frequency and the low severity combined total. And then there is we use bootstrap sample from the historical file to build a model to try to replicate the stochastic event. So it's a random component. We model the low severity and the high severity separately, and then combine to make the final model. Next slide, please. So the data in this case, in this exploration, we use the MTDS data. We focus only on forest-only land. We extruded the 5 pixels from the edge of the existing burn. The reason we do that is try to minimize the effect of fire firefighters' effort to put off fire. They build those. What's the term for that? It reduces the human footprint on the fire security. Sorry. Then the interest there are 2 separate models. One is low severity was the all other class, and the high severity was other class. So there were those 2 separate models, low and high. So in the end, we want to find the refugia area. Next slide. This is a detailed description of what how we did this process. So for each year, we model it separately. The model is using a random forest model. From the low versus other or high versus other, there are those 2 binary classes. We'll have for each model, we have 5,000 random sample from each classes. So basically 5,000 sample from low severity, 5,000 from other class. Build the model and replicate 50 times for each year. Then from all the combined 50 random forest run, we aggregate to an annual output. 50 runs is what a larger run might be better to more simply try quantify the stochastic component in there. That 50 seems stable enough over all the years we run. The same process will repeat for the high severity versus other class. The same modeling approach. Next slide. So the variable in this case, we are looking for the topographic template. So vegetation is considered as just a binary vegetation, yes, forested or not. Climate, this is the topographic variable derived from NED data, 10-meter data. This is the David Searbold published paper in 2020. Oh, I forgot the exact date. Next slide, please. Ray. So we want to include vegetation is considered a constant. We incorporate the raised climate norm model. So this shows the correlation among the variables we're going to use in the model. So the highest correlation between climate norm predicted fire relative likelihood with Chile data is 0.7. I think it's not high enough to raise the concern. So we went ahead using all these 5 variables in the model. Next slide, please. So this is diagram show what they described. So we combine the 2 topographic variable and the climate variable to build a low severity refugia probability and separately build a high severity probability. Then through model aggregation, we get the final refugia map. So together, this is the how variable importance from all the 1,750 random forest model. So overall, the Chile index has the highest contribution, and with climate norm has the least amount. This slide is showing for we model each year separately. So one thing to know is look the color represents from low to high. So from red from red to green. So the first thing to notice is that the refugia predicted the model build for each year. They vary a lot. They're not consistent. So this is, I think this is reflecting the ephemeral refugia. If the model for each year is performed reasonably well, but over time they're not consistent. So what we are looking for is the long-term persistent refugia. So this is when we aggregate all together, how often a pixel is being mapped as a refugia. That's we derive the right-hand side relative probability over the 35-year period. Next slide, please. The random forest model, when we combine the, it didn't produce a response code. This is a kind of a simulated response code to try to understand whether does the model perform as we expected. So, it seems the model performed match our expectation. Chilling index represents how much like the solar radiation, how hot the surface could be. So as the hotter it gets, it will be more less likely to be a refugia. So that's reflecting the downward trend from 0 to 0.5. But then, so I think that part is reflecting the low frequency part of our refugia component. So that's the contracting from 0.5 to up. So the hotter it gets, it also increases the likelihood to be a refugia. I think we are hypothesizing that as it's more likely, it's hotter, it's more likely to be burned. It frequently burned, subsequent fire will have low severity. So the left-hand side show the low frequency, the right-hand side show the low severity response to the chilling index. Similarly for MTPI, the lower value, that's usually the lower valley, bottom, narrow valley. So those are to be have high probability to be refugia, while those higher slopes are less likely to be refugia. And that's it. The climate norm that has a similar shape with Chile, I think that also shows the low low frequency on the left side and the higher frequency on the climate about 0.5 that frequently burn. The subsequent burn will have low severity. Next slide, please. Right. So this is the result that show the map. This is the map of the first slide. I want to draw your attention to the black box. That's the area, if you remember from early slide, that's the area had it's the red in the relative fire probability surface. So they tend to have burned more often and they're frequently burned. But over time, with the frequently burned, then they will be low severity. So that was over time. By the end of the century, our map showed it had a higher probability of fire refugia. While the coast rate, so that's those blue color in there, it's representing low frequency component of our fire refugia surface. Next slide, please. So far, all our analysis are based on topographic variable and the data, or from NASA's data. So we map this. What does it mean? for we want to understand what we are mapping to. So we start to exploring, try to link the CMS product carbon. And in this, we show the example of using the JEDI data. For just to basically relating the JEDI kind of height information with refugia. So we look at the two ecoregions, the coast range and the cascade. So on the coast range side, this one it's we don't know exactly how to interpret this yet, but our hypothesis is that the coast also please also notice the wider shade area, the larger uncertainty for the taller trees in the coast range. I think that is also due to there are fewer taller trees in the coast range. This shows that the shorter trees has a higher probability of being in the refugia area. One of historically there are not much fire happening in the coast range, so we're going to explore this with the different CMS carbon product, and also Sean simulated the different projects that provide a good framework to estimate the carbon over time. We want to use that to fully understand what's happening in the coast range for this relation. On the cascade, data completely is what we expected. As taller trees, they tend to, even they are more likely to be refugia, they are more resistant to fire. Even when they burn at the low severity. So another way to say is the cascade shows the relationship of severity, and the coast range still showing the frequency, but we still need to untangle what's causing that relationship. Maybe you have any idea, thought, please let us know on how to do that. This is the this slide shows. Go ahead. It's a repeat from the previous slide. It shows highlighting. Previously, it showed the trend over all the time period. So with one class, this one will break it into three categories: low, moderate, and high, based on the refugia probability. So low is 0 to 25, 0.25, 0.25 to 0.5 is moderate, about 0.5 probabilities we call it high. This is the ASO is northern spotted owl. This is showing in the northern spotted owl nesting roosting habitat the trend over time for predicted refugia. What's the temporal dynamic? You can see the high probability is stable with slight increase over time, while the other two categories show the also stable should be hello?
I can hear you.
We
Oh,
hear you. We hear you.
oh, okay. There. Sorry. I hear my headphones get some strange noise. Next slide, please, Ray. So, so on the previous slide showed the temper trend, but with the overall the trend, it's hard to see any pattern. This is shows the annual change out of the refugia category. So before 1990, before it's listed, we see they're mostly in the negative territory. So once they all are listed, so we see the refugia area keep get increasing until and mostly in the positive range. When some big fire happened, like in 2003, then we see big drop. So that's to highlight the refugia is not consistent. The fire, even map of the fire refugia can also be burned given under the right condition. So all those big fire years in 2003, 2008, they show the big drop. Then without the fire, we map the refugia area mainly in the positive increase territory. One part, this is due to their larger trees or relatively larger trees, they tend to grow faster. You will notice the downward trend from 2010 to 2000, the downward trend, except for besides those many, that's where those many large, from 2010, the fire, the burned areas that pick up. There are more fire occurring in this region, just causing the refugia area to decrease. Great, next slide, please. This is I want to show a real example of a late succession reserve. So and map the refugia. So left side is the refugia probability in the three category. The middle is in 1993. Okay, the reserve where the reserve are between 1993 and 2021. There fire happened for this area. So you see all those remaining still as a nesting roosting habitat. They are mostly in the reserve in the high probability of a fire refugia. This is I think this highlights two things. One is refugia, mapped refugia, they are not bulletproof. They still can be burned. But what the mapped at high probability of refugia, they are more resilient than other areas. So with this example that showed that what happened on the landscape. I think that's our last slide. Thank you for your paying attention. Questions?
Thank you, Yang, and thank you, Ray. So let's see. We're back. Let's see if anyone has any questions. You can either post them on the chat box, or you can unmute yourself and make the questions directly to Ray or Yang.
Yeah, this is Werner Kurtz. Thanks for the nice presentation. In your abstract, you made reference to reductions in area and reductions in carbon stocks, but you did not speak about reductions in carbon stocks in your presentation. You did have a slide where you said you never get any breaking news that these forests are carbon sinks. So my question to you is, given the area changes, given the extent of the fires, do you really believe that these forests are still carbon sinks net over the period that you have described?
I think they are. There's the relationship between northern spotted owl habitat, which is what I mostly focus on in old growth, is highly correlated with the amount of carbon, the above ground biomass, and even with the loss of forest, of that type of forest on federal lands in the last 25, well, the first 25 years, actually, we showed a slight gain. So I would say there's been a positive sequestration in the first quarter century of the plan. I'm more uncertain about that, given the big fire seasons from the last few years, where over 1 million acres has burnt within that area. 2 million acres in 2020, which was our biggest, most recent contemporary fire season. So, yeah, so there's a little bit of uncertainty as to whether or not, we're going to get positives or negative numbers on the carbon.
But you haven't analyzed those data yet.
No,
Okay.
my focus is, I think Dave Bell from Pacific Northwest Research Station is focusing on carbon for this area,
Okay.
but personally, I have not.
Thanks, Ray. Appreciate it.
So just additional comment on that. Sean Healy is leading is a Jedi related CMS Jedi based change estimation project. So we are actively evaluating the carbon change for this region, basically for the past using linked Jedi data with Landsat together to quantify how much carbon was being lost and how much carbon was gained year by basically on the annual time step.
Thank you.
Thank you. Thank you, Ray. And yeah, Jan was mentioning there is Sean Healy has a CMS project that was from 2016 that is basically piloting a Jedi-based forest carbon monitoring, reporting, and verification tool. So, in another question from Johanna Chazaro Cortez, she asked if Landsat time series are being used for fire monitoring, and if so, what findings are you trying to get from them?
I'm going to just briefly reply to that and let Jan talk about it, because the answer is yes. The Northwest Forest Plan uses products from the Landscape Change Monitoring System, which is based on Landsat time series to track forest disturbances. And I'll just let Jan provide a little bit more information on that.
Sure. Landscape Change Monitoring System is first service led monitoring system using Landsat time series. Sean Healy is the lead PI on this project. So basically, we are using ensemble methods from Landsat time series from different change detection algorithms, monitoring land not only for disturbance, but also for forest recovery process. So from that process, what we have is yes, Sean just posted a link to the LCMS product. So we have disturbance, forest change, land cover, land use on annual time step. So those are the forest change information combined with what I mentioned, the Jedi carbon estimate. Layering those two together, we can make a more precise estimate quantification of forest carbon change over time and how it affects fire refugia. What's the fire refugia structure in terms of carbon, in terms of disturbance regime? Those all can be quantified, linked together by marrying those two projects together.
Thank you, Yang. I have one question here, but I was going to ask if there is someone else that wants to make the question directly to Ray or Yang.
Yeah, hi, Ray. This is Peter Griffith at Goddard. I was taken by in your intro with Greeley's comments about the 1620 virgin forest concept, which I can sort of see you might be grinning a little bit there. That of course Greeley was ignoring that most of those forests were actively managed by indigenous people with controlled burns and prescribed burns, and had been for probably thousands of years at that point. And I'm wondering what the Forest Service today is maybe actively doing to incorporate some of the deeper knowledge about management of forests over long time frames that come out of that knowledge base.
Yeah, thanks, Peter. That's a really good observation. And yes, indigenous inhabitants of the continent were familiar with the use of fire in all of the forests here, even in the Pacific Northwest. There's recent research that's coming out that acknowledges that role. And also, there's some acknowledgement that the suppression that was pretty much institutionalized, the forest fire suppression in the early 1900s has excluded this natural component of the forest fires for a lot of decades. And there's also the understanding that it has altered the natural fire regimes or the fire regimes that existed prior to the European settlement period. And so there's discussions about how do we get back to this more natural fire regime through the use of prescribed natural fires or managed prescribed fires. There's a broad acknowledgement from the folks that I work with that fire is part of the forest ecosystem here. It always has been for a long time. So when we're talking refugia, fire refugia, there's really no piece of the forest in the Northwest Forest Plan that has never burned. It has always burned. It's just a matter of frequency. And as a result of decades of fire exclusion, we're starting to see, I think, a little bit more high severity fire than was probably there naturally. And so that's something that the agency is aware of, and but I'm not going to predict the future. It's very difficult to get to a point where, well, from a management perspective, to treat the millions of acres out there with fire, that's very, very complicated, very expensive. So right now, we're just managing mostly the wildfires as they occur.
Thank you.
And I'm speaking just for the area that I work in. I'm not that familiar with what the Forest Service is doing in other parts of the United States. I do believe in the East Coast there's actually a very active prescribed fire program.
Thank you, Ray, and thank you, Peter. So one more question, more on the policy side. So Tom Chi, he asks, what do you hope for the work to influence policy work or commercial work? And I will add, Ray, you mentioned that you have been engaged with several stakeholders, and that includes the Oregon Department of Forestry, I think. So if you could also talk a little bit about that, and if there is any opportunity to engage further stakeholders like state agencies in Washington or California.
Okay, yeah, so we're actively doing that currently. We are working in partnership with Washington Department of Natural Resources, Oregon Department of Forestry, to take another look at the Northwest Forest Plan area to try to find the areas that are less prone to these high severity fires or places that burn less frequently. So the stuff that Jan presented. So that is actually ongoing, and it's pretty active collaboration. I know my partner, Andrew Yost from Oregon Department of Forestry, he shares the information from this with the folks that make the policy in Oregon State for forest management. So this look at, I guess what I was hoping is, what we're trying to do is kind of broaden the perspective, I suppose, on the fire equation. So most of the focus has been on places that have burnt. What do we do after they burn, or places that burn a lot? What do we do to make future fires less severe, to make the forest more resilient in those areas? But there's been very little focus on places where we have the highest likelihood of maintaining carbon into the future. So those would be the refugia. So it's my hope that we're shining some light on that part of the spectrum.
Thank you, Ray. We have time for one more question or comment. I don't see anything else here in the chat. So I don't know if anyone has any other question or comment for Ray or Yang. If not, Ray, I will leave. We have maybe like 1-2 minutes. If you want, we have one more question here, and if you want to give any final thoughts, we have one question like if the plan is to stay focused on the US, or will you expand to the rest of the world?
Well, my focus is definitely just a little part of the United States, but I think what we've demonstrated here can have broad applications. The NASA CMS program obviously does a lot of monitoring of carbon at very broad, even global scales. There's science out there that exists that predicts the likelihood of future future fires under climate change, and so I think it's just marriage of those two types of sciences: the carbon monitoring science and technology with the climate monitoring and prediction technology. So I would say that this could be replicated elsewhere in the globe using those two broad categories of science and technology.
Thank you, Ray. So if there is no other questions, let me know if there is any other question, comments. If there is not, then I would like to thank again Ray and Yang for their time and presentation in today's seminar. Thank you for everyone for joining. We're gonna have the recording and the slides of today's seminar in the CMS website. I included the direct link to where we archive the recordings. I also included, because someone asked for it privately, I included the link for the ERL, Environmental Research Letter, call for papers that we have ongoing to the end of the year. So please feel free to go there and find more information. And if you have any questions, just reach out to us. I think everyone has my email. So yeah, feel free to do that. Thank you, everyone. And thank you, Ray, again. Thank you, Yang, for your time.
Thank you, Adil. Thank you, everyone, for joining in today.
Thank you.
Thanks.
Bye.